Hello everyone, welcome back. We are now into the last week of lectures for this course, and I'm very glad that you've stuck on with this course for this long, and I'm hoping that you're learning a good bit from this course. So this week is going to be about other alternate platforms. So we've looked at Hyperledger Fabric and Hyperledger Composer earlier in this course, but we're going to look at a few other platforms this week. So we're going to look at specifically Ethereum, Quorum, and Corda. So I'm not going to spend too much time on these, just one lecture each. Corda will spend a little more time, 2 lectures on Corda. So we'll look at some of these platforms, some of their pros and cons, different design ways in which they are defining or designing primitives for smart contract use, and we'll see what some of their advantages, disadvantages are. So this lecture is we're going to talk about Ethereum. So Ethereum is one of the hottest blockchain platforms today. It was founded by Vitalik Buterin, and it was back in 2013. And he felt that the Bitcoin scripting language was way too restrictive for smart contracts. So it was primarily intended as a means for executing smart contracts in a decentralized fashion. So that's how it started. And even today, that's one of the biggest uses of Ethereum. The smart contracts are known as dApps, or decentralized application, and they run on a Ethereum virtual machine. So we'll see some details of this. Ethereum itself is an overloaded term, right? It refers to the public network. It's similar to Bitcoin. There's a public Ethereum network that runs, and there's a set of peers that run this network. It can also be a private permissioned version of Ethereum. So it's possible to take the Ethereum code base, run it as a private network or a permissioned network with just a few nodes. So that's also possible, and Ethereum is referred to it in that way also. Not just a public network, it can also be a permission network. And it's also the open source software behind Ethereum is also referred to as Ethereum. So it's really overloaded in that sense. It does have a native cryptocurrency called Ether, similar to Bitcoin, right? So Bitcoin is also an overloaded term. Ethereum has Ether as native cryptocurrency. And today, as I checked just a few days back, the mainnet for Ethereum has over 16,000 nodes, and I'm not sure how many are really full nodes, but there are a very large number of nodes now running the public Ethereum network, and the average block formation time is about 17 seconds, which is significantly better than Bitcoin, which is about 10 minutes today. So Bitcoin takes 10 minutes for each block. Ethereum takes roughly about 15 to 17 seconds. And miners today get 5 Ether plus all the transaction fees for the transactions in the block they mine. So it also uses proof of work similar to Bitcoin, but we'll talk about some of that in due course. So there is a reward for mining, which is 5 Ether, and the miner who finds the proof of work challenge, solves the proof of work challenge first, gets also the transaction fee. So now Ethereum is being developed by Ethereum Foundation, which is a Swiss non-profit organization, but it has contributions coming from a much broader community. So there's a big community behind Ethereum that's contributing to the code. So just a very brief history of how Ethereum has evolved. So the Ethereum white paper came out in late 2013, and the project itself was announced in 2014. Then there was a yellow paper with more details that came out in mid-2014. And then the Ethereum Foundation was established, and in July 2014 was the first initial coin offering. So Ethereum was perhaps you're probably hearing about initial coin offerings, ICOs. They are really a rage today, with people creating a startup and coming out with their own cryptocurrencies or coins for various blockchain use cases. And Ethereum or Ether was the first initial coin offering back in July 2014. So it had this good technical backing, a yellow paper, white paper, and a Ethereum Foundation before they came out with the ICO. Right? The live blockchain came out a year later, and since then it's actually seen a rapid growth in the network itself, in the valuation of Ether. It's really grown multi-folds since then. And several large financial institutions have looked at variants of Ether for permissioned versions for enterprise use cases, and that has also become quite popular. And we will look at one such variant in the next lecture, which is Quorum, and we'll look at some of the properties in Quorum. First production ready version was released in March 2016, so roughly a little over 2 years back. There have been various attacks on, I wouldn't say Ethereum itself. The Ethereum itself has been fairly solid. The blockchain platform has been solid. But on the smart contracts running on Ethereum, there have been various attacks on them. The most notable of them was the DAO attack, which caused several millions of dollars to be siphoned off from the smart contract that held that value. And as a result, that actually ended up in a hard fork of Ethereum. So people actually ended up reversing certain blocks in the blockchain, going back in the past and then creating a fork from there to not have this hacker take away all their money. Right? So that was a very momentous occasion where people actually undid something on the blockchain. The community decided they were going to go back. But there have been a lot of security attacks on Ethereum smart contracts over the last couple of years. And last year, in March 2017, the Enterprise Ethereum Alliance was formed. And this was again looking at how Ethereum can be used for enterprise use cases and how some of the shortcomings of Ethereum for enterprise use can be overcome. So we'll look at that briefly in the next lecture as well, before we talk about core. So just a high-level view of the Ethereum architecture. What are some of the constructs? So the Ethereum client, it runs. So every Ethereum node runs an Ethereum virtual machine, and all the smart contracts run within this virtual machine. And clients can connect to this the Ethereum client applications can connect to the Ethereum client using an SDK. There's a Web3j SDK for it. Transactions have a particular format, of course. It has a to address. Who are you transacting this with? So this, just like Bitcoin, it's a particular recipient is mentioned. There is data pertaining to the smart contracts. That's also mentioned there. What is the value of Ether you're going to transfer to the recipient? There's a nonce and there's a notion of gas, which we'll see shortly. And of course, there's a signature by the transactor. So the user who is sending this transaction is going to sign the transaction and send it to blockchain. So note that Ethereum actually does two functions. It's actually going to transfer value or Ether in some sense. And it's also going to execute, it can also execute a smart contract function. And that smart contract can hold data on the blockchain. And there is a Ethereum network of many such nodes all interacting with each other. And these nodes are the ones which run consensus and determine what block of transactions should be added next to the blockchain. And this consensus is through proof of work, similar to how Bitcoin did it. There are alternatives being considered as well, but for now, proof of work is what is being used by the Ethereum blockchain. And there is a proof of stake algorithm that's going to come out later in the Casper release. When a node receives a block, what the Ethereum client will do is it's going to execute all the transactions in the block in sequence, and it will then update its ledger once once it knows that a block has been added. It's possible that because it's getting this block from multiple people, redundant executions are possible, but they're hoping that a notion of sharding will help reduce this. So we'll look at sharding right at the end of this lecture very briefly. So the underlying database that Ethereum uses is a level DB. So it just has a basic key value store available to smart contracts to store state information. And the contract bytecode is also stored on chain. The list of blocks and the state data, this is similar to Fabric. Both the list of blocks and the state data is stored on the blockchain. So now let's look at a few notions, right? What are accounts, what is gas, and the notion of transactions in Ethereum, right? So Ethereum really has two kinds of accounts. One is called an externally controlled account. So this is like I as a user of Ethereum, I can have a wallet, an account, and have a certain balance in that account. So that Ether balance is held in that externally controlled account. So there's a user who owns this account in some sense. And it's possible to transfer Ether from one externally controlled account to another externally controlled account. So this transaction is pretty much just identical to what Bitcoin does. So you are going to have a certain set of inputs, a certain set of outputs, and you're going to show that the inputs are all unspent, so it's basically a UTXO model, and you can transfer Ether from one account to another account, very similar to Bitcoin. But that's just one part of the story. The other kind of account that we have in Ethereum is called a contract account. So this is really for smart contracts. So every smart contract will have a contract account, and it will have an address very similar. It's a similar looking address to an externally controlled account. So both of them have addresses, but a contract account specifically refers to a smart contract, and it does not refer to a particular individual or an externally controlled account. And what is also possible is for transactions to both have refer to an externally controlled account as well to a contract account. So I can transfer some ethers from one account to another. I can also invoke a particular smart contract specified at a particular address. And that smart contract will of course run a particular function defined in the contract, and that function can update state information on blockchain. So that's the distinction from Bitcoin itself, where it's just not Bitcoins being transferred from person A to person B. In addition, you can have a smart contract function that operates on arbitrary state information, and the state information is basically a key value store. So you can define your own keys and have values for those. And apart from invoking one contract, these contracts can also invoke other contracts. So similar to Fabric, where one chain code can invoke another chain code, one contract can call another contract, and again there can be a transfer of balances between contracts as well. Now all of this invocation of transactions or invocation of smart contract functions actually incurs a transaction cost, and this is really to ensure that people are not, because this is a public permissionless system, we want to ensure that people are not randomly spamming the network with invalid or wrong transactions, right? So people just don't want to take away, maybe it could be a denial of service attack also, right? I could just randomly access transactions, access call functions, and sabotage the network, right? To prevent that, Ethereum has the notion of gas. So for each transaction, you will have to spend some gas. So this is the fuel for the transaction, if you will. And unless you pay in terms of this gas price, unless you pay for the transaction, you can't execute the transaction. So each transaction is also going to have a particular gas price. So I'll say that, okay, for this invoking this transaction, this is the gas I'm going to pay. And you can also set a limit, because you don't want your balance to be depleted. Like, what if the contract really runs for a long time for whatever reason, and you lose a large amount of money, right? So you don't want to do that. So the gas has both a price and a limit, and the gas fee is really paid using Ether, right? How much ever is the gas, there is a certain price. So there is a mapping from gas to Ether, and you have to pay that much Ether to invoke the transaction. So this is really the gas price is really borne by the sender of the transaction. Looking at the smart contracts themselves, Ethereum allows or has multiple languages in which these smart contracts can be written. There's many languages, Serpent, Viper, etc. But the one that's most popular is Solidity. Solidity is an object-oriented high-level language. It's very similar to JavaScript, and it is executed inside an Ethereum virtual machine. So any of these languages, what they do is they compile into a standardized bytecode. So this looks something like assembly, right? So push 10 and you could load data, things like that, right? So it's really close to assembly. It's a really bytecode, and this bytecode runs in a Ethereum virtual machine. So this bytecode is what is deployed onto the blockchain network, and this compilation is kind of outside. The syntax, as I said, is similar to JavaScript. If you're familiar with JavaScript, it's statically typed, and it supports multiple inheritance. Yeah, it also supports complex user data types through structs. So all this is very standard object-oriented programming principles. The core languages that have been defined have all been defined for or keeping in mind the Ethereum virtual machine. And the Ethereum virtual machine itself is a bit locked down in some sense. So you can only perform a certain set of things. We'll come to it in the next slide. The Ethereum virtual machine has certain limitations and deliberately has certain limitations. And the languages also reflect that. Right? There are only few things you can do. For instance, even basic string manipulation is not supported, but it's only supported through libraries. So there'll be other libraries that you can use for string manipulation, but the languages themselves do not support it. There is a browser-based IDE for Solidity, and that browser has an integrated compiler. And the Solidity runtime environment can run without any server-side components. Very important philosophical notion for Ethereum smart contracts is that the belief is that code is really law, right? Whatever is in the code is the right thing, right? So there is no auditability or governance. There's no other authority that's going to govern this piece of code, right? Whatever this piece of code is going to be executed in a decentralized fashion. And many a time, this philosophical notion, while it's great from a notion of philosophy that there is no authority, there is no governance, while that is great to hear because it's completely decentralized that way, in reality that becomes problematic. Because what if a hacker, as has happened in the past, if a hacker comes in and steals data because your smart contract had a vulnerability in it, right? It allowed the hacker to steal the data. Then what do you call it, right? The code, if you say the code is law, then the fact that the hacker leveraged a vulnerability, the vulnerability, is it then a feature, right? So that becomes a philosophical question then. The problem is that there is a specification typically of a problem that you want to solve, and there is code that tries to write a solution to that specification. And typically that code is written by a human and it's fallible, right? So you could make mistakes when writing code. There are bugs, for instance, in code that you write. And smart contracts are going to be no different. There will probably be bugs in smart contracts. And if code is really law, then you're saying buggy code is going to be believed and enforced upon all the time. So that causes problems and also cause for a lot of the debates that have happened in the community, whether this should really be the case or whether there should be some governance around it. Moving on, coming to the Ethereum virtual machine itself, it does support a Turing complete language. It's a 256-bit virtual machine, and the computation is intrinsically bounded through gas. So I provide a certain amount of gas, and if the gas is consumed, then the contract execution, the smart contract execution will stop, right? So that way, if a transaction or a smart contract had unbounded execution for some reason, or you provided certain inputs on which there was unbounded execution, by design of having this gas and having a limit on it will ensure that the contract does not run indefinitely. So this allows termination to be definitive within a certain period of time, and it allows execution within the EVM bytecode. So the EVM defines about 70 opcodes, and you're limited by that. So that is only the set that's allowed, and these set of opcodes are interpreted by an interpreter. And for each opcode, each of these 70 opcodes, there is a specific gas value that is defined. And this gas value is set based on, in some sense, roughly the difficulty of that operation. And what are some of the operations? It could be, for instance, arithmetic functions like add, subtract, multiply, divide. It could be logical operations like and or kind of logical operators. It could be conditional statements like if then else. It can be send, right? I can send ether to another address. So all of these are opcodes. And for each opcode, based on the computational complexity on a traditional processor, there are gas limits that are set. So you could say that, okay, if I'm going to make up numbers, if costs 40 gas, or and multiply operator costs 30 gas, right? So based on the complexity of the operations, gas is specified. And that gas, so based on all the operations in a transaction, let's say a transaction has 10 such operations, you will add up all the gas for all the operations, and that is the gas necessary to invoke that transaction. And that gas has to be paid for using Ether, which is the inbuilt cryptocurrency in Ethereum. And if you want to get a sense of what kind of operations are allowed, think of an old smartphone, right? Back in the early 2000s, perhaps, right? Those old phones, whatever computation you could do on those old phones, is what you could do on an EVM. For instance, I would really cringe away from doing like complex crypto functions inside my smart contract. In contrast with Fabric, we are providing you the ability to provide crypto functions within the chain code itself, whereas in EVM that will be very hard to do. So here's an example of a basic Solidity code. So I'm not going to go into details, but just to give you a feel for what this looks like. So standard object-oriented programming similar to JavaScript, right? A contract is defined. You can import other contracts also, so you can reference other smart contracts. So in this case, we are actually importing a KV store contract. You can have transaction events. So these events will be emitted when the transaction executes. And so if you this is the definition of the event, and within the function, this is the smart contract function that's going to get invoked in a transaction. You can also fire these transactions. So at different points of the function execution, you can fire transaction events. Then you could have modifier functions. These ensure that execution proceeds only if a precondition is met. You can have a constant keyword added. So this is for read-only transactions. So this is for like a query operation, and you can have return types. Right? So this is roughly the structure of a Solidity contract. So there's a contract. It can have multiple functions. You are defining some structs or data objects. You can refer to other contracts. You can invoke other contracts. All that is possible. So in some sense, it is to Turing complete, but the sophistication is limited, is deliberately limited, because you don't want to allow non-deterministic execution. You want termination to be guaranteed. So because you want some of those properties, it has been deliberately restricted. Okay, what are some of the patterns, right? The non-trivial decentralized app, you should read decentralized apps, by the way. It should not just it's actually decentralized, not distributed. The data and logic can actually span multiple contracts. Typically, there could be 5 model types. One is a database contract. This is going to have all the data objects in them. One is a controller contract, which operates on the database contract. So this will be the controller on when or what to be written onto the ledger. And one controller contract can work with multiple database contracts just for separation. And there's a contract managing contract. So this manages the contract itself. There's an application logic contract, and there could be utility functions defined as a separate contract. So collectively, all of these contracts could be a decentralized app in Ethereum. And the decentralized apps typically also have a graphical user interface. And this allows users, even those who are not so familiar with blockchain or the intricacies of smart contracts, the GUI will allow them to interact with the contracts very similar to how Web 2.0 apps do. Right? So it gives you a HTML interface or a JS CSS interface for interacting with smart contracts. There are a lot of additional capabilities that are being added or have been added and are being added to Ethereum. There's a lot of innovation going on in the Ethereum blockchain itself. So first, as I mentioned, there's proof of stake for saving energy consumption. So with Ethereum, currently it does use proof of work, which is it consumes a lot of energy because you're doing a lot of hash computations. Instead, there is a proof of stake, an alternative algorithm that consumes lesser energy. So that's coming out later. It's not yet there. With Ethereum, while the block formation time is significantly lower, the throughput of Ethereum is still fairly low, few tens of transactions per second. Okay, what are some of the additional capabilities? Right. So the first one is there's a Swarm file storage that's basically allowing decentralized file storage to be built inside Ethereum. And what it does is it uses contracts themselves to encourage cooperation among nodes. So let's say I want to store a particular file. I can store that in Ethereum, and I can pay the nodes who are storing it. So the contracts themselves will manage both the storage as well as the payment for that storage. So that's being integrated into Ethereum. The next one is whisper messaging. So this allows secure private communications amongst maybe a subset of entities, right? So it inherently supports unicast, multicast, and broadcast. And what it does, it actually encrypts messages. It's simple in concept, right? It's just encrypting messages, and it's announced to the network off chain. Right? It allows contract-to-contract communication apart from just person-to-person communication. So Whisper has been integrated into the Ethereum protocol. But it does, because of all the encryption and messaging complexity, it does have high latency and low bandwidth. Right? So that's important to consider. It's also possible to use masks and filters to narrow down the topics of interest. So each of these messages, you can put them into topics, right? And you can probably just filter these messages based on topics that you are interested in. And for any particular user or a client, you won't be giving away what topics you are interested in, what topics you are seeking to find out. Right? So that's on the secure messaging front. So Raiden is a very interesting concept built on top of Ethereum. It gives you a notion of state channels. So the idea here is with blockchain being rather slow, commit latency is fairly high. With Bitcoin, it's 10 minutes. With Ethereum, it's 17 seconds or 15 seconds. But that's still a significant period of time. Today, our digital transactions go through much quicker than that, right? So what state channels allows you to do, it's really a payment network. But what it allows you to do is just have some proof on blockchain. And actual payments happen on a separate off-chain channel, right? So this is not similar to channels in Fabric, but it's a different notion where two or more parties can get into a particular channel. They can exchange messages between each other to exchange value. So they could exchange, for instance, Ether amongst themselves, but they don't go to the blockchain for every one of those transactions. To just give you a very vague or a very high-level example, let's say I'm going to go to a coffee shop. I go there every day, every morning, I buy coffee. If I were to, for instance, pay for that coffee in cryptocurrency, then every day I have to make that transaction, and each of those transactions has to be recorded on blockchain. But typically, the coffee shop and we kind of trust each other, right? We are known entities. Unless there is a dispute, we don't want to overburden ourselves with going to the blockchain every time. So what I could do is I could say I have 50 rupees in my, or whatever, right? Let's say I have 500 rupees in my account. I can go to the coffee shop. I can just exchange a message saying, here, I've signed a message to you saying I'm purchasing a coffee from you. Here's 10 rupees, right? I can do that over 100 days and collectively submit that whole set of transactions onto the blockchain. If, for instance, I try to run away without paying for my coffee, then the coffee shop will be able to go to the blockchain, prove to them that I have actually cheated. So there'll be penalties imposed, and that disincentivizes either of us from cheating. So that's really a payment channel that is outside the blockchain itself. There's only some minimal information recorded on the blockchain that will be useful for dispute resolution or serve as a proof of transactions, but nothing more. Right? So it really allows you to batch transactions together and send them and commit them on blockchain. It's a very interesting notion to enhance the performance of blockchain platforms. So you should definitely check that out. RAID and state channels. This is similar to Bitcoin, the Lightning network in Bitcoin. So you should check that out. So the next capability is that of sharding or having transaction groups. So what is possible? This one is still under implementation. It's not yet out there with Ethereum. Nodes can be partitioned into multiple transaction groups. And each transaction group only processes certain transactions or only stores certain amount of data. So that's really similar to the sharding notion in databases, where the database can really be a distributed database. And with sharding, each node in the database stores only certain partition of the data. Right? Similarly, with blockchains also, they're introducing sharding, where certain peers hold certain data, and I don't have to hold all the data in the network. There are, of course, you do this at a reduced security guarantee on how many nodes need to be attacked for you to take over at least that transaction group. So you have to take over a smaller, there's a lesser security guarantee there. But there are ways to dynamically figure out what is the trust level in the network. So there is a lot of innovation going on in this space, right? I want to figure out what is the trust level, and based on that I create my transaction groups. I do the sharding based on that. So there's some interesting concepts going on there. So Ethereum does have its own limitations. It has a nice set of features. It's great for smart contracts, for transactions that involve exchange of ether between parties, but it does have limitations in its smart contract logic. Right? Smart contracts are the state is bound to a specific contract. So the state and the logic, if they are in the same contract, or the same contract, it reduces maintainability. What if I want to update the contract logic, right? Then one has to manually copy over the state from the previous contract version to the new contract version. So all that becomes problematic. To some extent, the separation of state contracts and the logic contracts that I talked about in dApps, which is typically followed, it helps mitigate this. So that's a design pattern that people have found out, that they want to separate the logic from the state. That way the logic can be changed and the state can be reused across. As I mentioned, it doesn't support string manipulation. It does not support returning complex data types. So only simple data types can be returned, and that becomes sometimes a cause of concern, because it doesn't give you the flexibility you need as a developer, especially working with an object-oriented programming language. And functions cannot contain more than 16 parameters and return values. So that also tends to be a limitation, because you can't have complex data types. So you have to, if you do want to send that across, you have to send each element separately, and there's a limit of 16. And that becomes a concern, right? Between not being able to pass complex data types, and between the fact that string handling is not supported very well, that becomes a limitation for a developer. Debugging distributed applications also tends to be harder, since the EVM today does not return very meaningful error messages. That's something at least I've personally felt using Solidity on EVM. And again, for inter-contract calls, when one contract invokes another contract, again, it's not possible to pass dynamically sized data. So it has to be fixed length strings. And the functions calling one contract from another contract also creates a new EVM instance. So let's say I have both of these contracts, so contract A and contract B, both of them are independently running in EVM instances. Now let's say if contract A calls contract B, it does not use the existing EVM instance, it actually creates a altogether new instance. Right? So that way many such instances are created, and if one contract is simultaneously called by many of these other contracts, then that becomes a performance bottleneck, because I'm spawning so many of these instances, redundant instances, I could potentially do with just one EVM instance. So there is a performance penalty when you are calling from, you're making inter-contract calls. Okay, so that's a high-level overview of Ethereum. There's good documentation that's available. There's a very large community using Ethereum today. There's a white paper and a yellow paper that I'll encourage you to read. And I mentioned state channels are a very interesting notion. So you can check out the Raiden network that's trying to improve the performance of the public Ethereum blockchain itself. Today the performance is not at a level acceptable for enterprise applications, and they're doing some of these improvements to assess that. But the Raiden is specifically for two-party or mostly for two-party two-party exchanges, and mostly used as a payment exchange. Okay, so that brings us to the end of the lecture on Ethereum. In the next lecture, we'll look at some of the Ethereum developer tools as well as Quorum, right, as a permissioned version of Ethereum. Thanks a lot.